Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're lucky to have Ohad Shamir here visiting us and giving his talk. He's visiting from the Hebrew University in Jerusalem. He's a PhD student working with Naftali Tishby on topics in the theory of unsupervised learning, which is kind of a hot and trendy and somewhat controversial topic in learning theoretic circles today. And today he's going to be talking about data clustering and stability for finite samples.
Okay, thank you very much. So this is joint work with Naftali Tishby, and it's essentially going to be an extended version of the talk I gave at the NIPS conference last week. If you have any questions, feel free to stop me anytime. Okay, so my talk is going to deal with cluster stability, which is a certain approach or technique in data clustering, and how we can apply ideas from machine learning in order to understand it better. So cluster stability is essentially an approach to deal with questions related to model selection in data clustering. For example, what type of clusters do we have in the data, or how many clusters we have in the data. And the basic idea is pretty simple. It's that the valid or correct models should be reproducible, in the sense that if we take our data set and randomly perturb it, or take different random subsets of our data and apply our clustering algorithm on each one, then we should get more or less the same clustering hypothesis each time. So let's just look at a very simple example to make it a bit more concrete. So let's suppose, for instance, that the data that we wish to cluster actually comes from this distribution, a mixture of 4 Gaussians in 2 dimensions, and I each time take a different random subset of my data and apply, for example, the k-means clustering algorithm. By the way, is everyone here familiar with the k-means algorithm? Okay. So if I do this, for example, with k equal 4, with 4 clusters, then each time I'm going to get more or less the same solution. The centroid is going to be more or less in the same place, and the solution is obviously stable. On the other hand, if I try it with a different number of clusters, such as k equal 3, then based on random fluctuations in the data, the centroids are going to be in completely different positions each time, and the solution is obviously unstable. Okay, so this is the basic idea of this method. Now, this idea has been around for quite a while. It was actually independently rediscovered several times on the different communities using data clustering, and there's a pretty significant literature on this method, including several articles in the past few years in areas such as bioinformatics and many others. And there are quite a few algorithms that were devised based on this idea, and there are different flavors. They usually differ in either how the data sets are created, whether we subsample or do random perturbations. Some algorithms use the idea of random projections, each time to project in a random subset of the features that we have. So this is one thing, and the second thing is usually how the clusterings are compared. So if the clustering is in the same data set, it's easy. There are many reasonable indices to compare the clusterings, such as the Rand or Jacob. Otherwise, we use various extension heuristics. So it can be a nearest neighbor or even some classifier, which we use in order to project clustering which we achieved on one data set to another data set. Now, over the past few years, there has been growing interest in the question of whether we can develop a theoretical understanding of cluster stability, really understand why does it work, when would it work better or worse, etc. However, quite recently, what seemed like a serious theoretical problem with this method was discovered. It was in a paper by Ben David, von Oxberg, and Pal in called 2006. Actually won best paper there. And we'll describe the problem. So first of all, the framework. So we're going to assume that our data is actually a sample, S, drawn IID from some underlying distribution D on a space X, which for concreteness, it can be, for example, the Euclidean space, but it's not strictly necessary. And our goal is to perform model selection, and specifically we're going to focus on the question of how many clusters do we have in the data. And we'll do this using the notion of cluster stability. We also assume that we have at hand some clustering algorithm A, parameterized by K, the number of clusters we wish the algorithm to find. And we'll assume that it is driven by optimizing some objective function. Now, there's also a certain definition of the stability of such an algorithm, which is a pretty reasonable one. It more or less reflects the kind of stability that algorithms in the literature use. So this stability measure is defined with respect to the clustering algorithm, AK, the distribution D, and the sample size M. So first of all, it's this expected distance between two clustering. So we take two independent samples of size M. We apply our clustering algorithm on each one. So we get two clusterings. And then there is a distance function between these two clusterings. And the stability measure is the expected value of this distance function. The distance function itself is essentially related to how much probability mass of D, the underlying distribution, switches between clusters when we compare these two different clusterings. And formally, for technical reasons, they define it a bit in a way which is technically a bit more complicated than what I've just said. But formally, it's the probability, if we take two random instances from D, then what is the probability that these two instances are in the same cluster under one clustering and in different clusters in the second clustering? Okay? Now, notice that the lower is the value of this stability measure, it means that the algorithm is more stable, because it means that on average, the distance between the two clusterings would be smaller. Okay, now if we believe that cluster stability is really a theoretically sound method, then we would expect it to work for not just for specific sample sizes, but for any sample size. And in particular, the authors of the paper I've mentioned studied what happens to this framework when we look at very large samples. Actually take M as it goes to infinity. And their main result was that cluster stability is asymptotically fully determined by the behavior of the objective function. And more specifically, if the objective function of our algorithm for any given K has a unique optimal solution with respect to the underlying distribution, then this stability measure that we've defined will converge to zero regardless of whether that choice of K fits the data or the distribution. And on the other hand, if the objective function has several optimal solutions, then the stability measure will remain positive above some constant C, depending on the distribution, again, regardless of whether our choice of K fits the data or the distribution. And just to show why this result makes sense, so let's return to the very simple setting we've discussed earlier. And suppose I change it just by a little bit. I take two of the Gaussians and put them a bit closer together. So obviously nothing material really changed here. I mean, we would still expect to get 4 as the answer to how many clusters do we have in our data set. And indeed, if we now apply k-means with k equal 4, we're going to get stability. But for large enough samples, if we do this with k equal 3, for example, then we're going to get stability as well. Because one of the centroids would always be on the two relatively closer Gaussians. So we're going to get absolute stability both for k equal 4 and k equal 3 for large enough sample sizes. And supposedly we can't use this method to decide how many clusters do we have even in this very simple example. So from this, the authors concluded that asymptotically, at least, the behavior of stability simply doesn't seem to depend on the parameters we care for. It only depends on these symmetries or unsymmetries in the objective function and not really on what we want. And although they've studied the case of asymptotically large sample sizes, you can still argue that for large enough finite samples, for any k, we're going to get a stability value of more or less 0 for any k, because in practice, usually we do have a single optimal solution to the objective function. So in general, this stability measure will converge to 0 as the sample size increases to infinity. Okay, so far for the background story. Now, yeah.
So to convince us that the argument made by Ben David and all is kind of intuitive and makes sense, you have to change the distribution a little bit. But their argument seems that it should hold for any distribution, also the distribution where everything is symmetric, right?
Yeah, it does. But what I wanted to show is that, well, the real problem is that it is the case where the stability measure converges to 0, because this is usually what happens in practice. I mean, this is a very nice and symmetric distribution of 4 Gaussians, but in practice, the distributions that we work on in real life are much more complicated. And the reason that for this case, k equal 3 is unstable, okay, so the result would still apply. The stability measure, even asymptotically, is going to be above 0 by some constant. But the reason for this is because the objective function of the K-means algorithm here has more than one optimal solution. And what this example shows that even if I make it slightly asymmetric by taking 2 of the Gaussians and putting them together, then I'm getting a stability measure which converges to 0 as sample size increases to infinity. So this is really the problem, that for any k, we have this convergence to 0. Yeah?
I remember the problem is that very often you have many suboptimal solutions which are nonetheless locally optimal. So can you say anything about
Yeah, okay. So in their work, they assumed that the algorithm is capable of finding the global optimal solution, which is admittedly a pretty strong assumption, but you know, the problem of optimization is a very hard one, and they didn't want to deal with it in their work. So right now we're going to assume that the algorithm is capable of finding the optimal solution. And many times, yeah.
looking at the sort of how bad the optimality landscape is and sort of looking at...
Well, as is well known, I mean, even, for example, in the case of k-means, it is possible that the algorithm would stay in a poor local optimal solution. So it's very hard to say something in general. It is observed, and there are some works on the subject, that if you have a distribution like, you know, a mixture of Gaussians where the Gaussians are enough well separated, etc., then with say with high probability over your random initialization, you would be able to find the optimal solution. So this is indeed a problem. There's a significant literature devoted to this topic, but in this work we put it aside and we look at the other problematic issue with this method. Okay. Any further questions? Okay. So, in our work, we're going to concentrate on essentially the same setting with the same definitions and all. In particular, as I've mentioned earlier, we're going to assume that for any k, we do have a unique optimal solution. So we get this universal asymptotic stability, convergence to 0 of our stability measure. And without foregoing any of the generality of this framework, we're going to see that this is actually quite far from the end of the story. Now, before getting a bit more formal, let's start with a few interesting informal observations. So let's start with an experimental one. So suppose I look at this very simple distribution, a mixture of 3 unequal unit variance Gaussians on the real line. I made them unequal, again, because I don't want these kind of symmetries in terms of the objective function. And now, suppose I apply k-means in this distribution and actually compute how does the cluster stability measure that we've defined look like. So if we do this with k equal 2, we get the following plot. It's a log-log plot where the x-axis is the sample size, ranging from a few dozen instances to almost 10 million. And the y-axis is the stability measure that we've defined. And you can see exactly as the theoretical results predict, we have what seems to be convergence towards 0 as the sample size increases to infinity. We can repeat the same thing with 3 clusters, the correct number of clusters in the data, so to speak. And again, exactly as the theoretical results predict, we have convergence towards 0. And again, if we do this with k equal 4, surprise, surprise, we get converges towards 0 as the sample size increases to infinity. So up till now, everything looks exactly as expected.
But it seems strange that on k equals 3, we get the same rate of convergence. I would expect to see much faster convergence.
Okay, so first of all, again, I should emphasize that this is a log-log plot. So the slope is only in the sense of whether it goes down as square root of m or 1 over m, and we'll get to that a bit later. Remind me if I don't refer to that. In any case, however, if I take these 3 plots and put them one on the other, then something interesting perhaps happens. So again, we have this convergence to 0 for both k equal 2, k equal 3, and k equal 4. But first of all, we can see that k equal 3 for any fixed sample size is much more stable than both k equal 2 and k equal 4. Stability measure is much lower. And what is perhaps even more interesting is that we have what seems to be this fixed ratio between the stability measures for any fixed sample size, which doesn't depend on the sample size itself, whether we're talking about a sample of size 100, 1,000, or 10 million. So this is already some indication which tells us that despite this universal convergence to 0, not all is lost, and there's still this structure remaining which perhaps can prove useful later on. Okay, so we're going to return to this example later on, but now let's take a completely different angle and make a theoretical observation. So let's consider for a moment the notion of generalization in clustering, in the sense that we have some sample S, which we know that it was sampled from some unknown distribution, and we can apply our clustering algorithm on it and get some clustering. But now suppose we want to know how well the model we found fits not the empirical sample, but rather the underlying distribution from which the sample came. Now, the relationship between stability and generalization is very well known in supervised learning theory in many different places. And maybe in the end I'll go a bit more into detail on that, but in certain settings, it seems that it is possible to derive a generalization bound where the cluster stability essentially governs the generalization term, or how fast we can generalize. And based on this link between stability and generalization, we might try to make some analogies. So suppose in the setting of generalization, we want to know which of the models that we consider generalizes best. Now, for this question, there is the whole literature on generalization bounds in order to answer this question. And notice that in general, if the hypothesis class is learnable, etc., these bounds will go to 0 as the sample size increases to infinity. If we have an infinite amount of data, the problem of generalization is meaningless. It's only for finite samples that the question of generalization is interesting. Now, in the generalization bounds, the important thing that we want to know is the rates of convergence, how fast we can generalize or how fast we can learn. So in order to answer the question here in the slide, we essentially want to pick a reasonable model with the highest generalization convergence rate. Now, in stability, we ask a different question. We ask which of the models is the most stable. Using this result from last year, we know that usually these measures will also go to 0 as the sample size increases to infinity. And now, based on this possible link between generalization and stability, we can perhaps conjecture that the important thing in stability is not this asymptotic limit of 0, but rather the exact rates of convergence. And essentially, if you want to know which of the models is the most stable, what we have to look at is the model with the highest stability convergence rate. Okay, so both this observation and the experimental one we've seen earlier leads us to the central idea or hypothesis of our paper, namely that for cluster stability, the important thing is not the asymptotic limit of 0 usually, but rather the exact convergence rate to that asymptotic value. So this is the central idea. The question, of course, is how can we actually quantify it and do something useful with it? Okay, so just a brief reminder. We've defined the stability measure as these expected distance between two clusterings based on two independent samples of size m, where the distance is the probability of two or a pair of randomly drawn instances to be in one cluster under one clustering and in different clusters in the other clustering. And we know that usually this stability measure will converge to 0 regardless of k, regardless of the model order we choose. So as a first step, we will need some kind of a theorem which will tell us whether these relative differences in the stability measure are empirically recoverable for any sample size. Yes, because as we've seen, these stability measures go to 0 as the sample size increases to infinity. Their absolute values become very, very small. But if there is this constant ratio between these values, we are interested to know when this would be empirically recoverable, because the stability measures become smaller, but on the other hand, our samples become larger. So we should be able to better discern between these values. So we're going to state this theorem now. So in itself, it's just a statistical theorem. So I'll present it, and then I'll explain why or how it's related to the notion of cluster stability. So suppose that x and y are two random variables with some arbitrary distribution bounded in 0 to 1. And let's suppose that their expected value has a certain ratio which is larger than 1 for some positive constant c. And for simplicity, we're going to assume that both the expectations are bigger than 0. And now we can define a simple empirical estimator of these expectations based on samples of size m. And what we can prove after some technical work is that the probability that the empirical estimator of x would be smaller or equal to the empirical estimator of y, despite the fact that the expected value of x is larger than the expected value of y, is upper bounded by this expression, which involves constants with c and n times the expectation of x. Okay, so the theorem itself is clear. Okay. So now, let's suppose that this x hat and y hat are actually empirical estimators of the distance between the two clusterings of S1 and S2 for two different values of k. Okay, so we took two samples, S1 and S2. We applied the clustering algorithm one time with a certain value k, and then with another value k prime. And if you recall, the definition of this distance depends on the underlying distribution. It's this probability over pairs of instances. We don't know this distribution, but we can empirically estimate it by taking, for example, m pairs of instances and see what percentage of them the event that they're in the same cluster in one clustering and different clusters under another clustering occurs. So if x hat and y hat are these kinds of empirical estimators, and suppose we can assume, as actually happens, that these distance values, which are random variables in themselves over S1 and S2, so they converge to 0 in probability as m goes to infinity, but at least with high probability, they have this ratio which is constant for any sample size. It doesn't depend on the sample size m. And if the rate of convergence to 0 is slower than 1 over m, we can use the theorem from the previous slide to show that the probability that we'll make a mistake, in the sense that we won't be able to discern which of the k's is more stable, actually converges to 0 as the sample size increases to infinity. So I'll just return a minute to the previous slide to show this. So according to our condition, this c is really a constant, which doesn't depend on the sample size m. And what we have here is m times the expectation of x. So if the expectation of x, in a sense, goes to 0 slower than 1 over m, then this entire expression goes to minus infinity, and we get the probability of error, which goes to 0. Okay, so the basic idea is clear. Okay, so now we're going to exemplify this on a certain simple example. Actually, the setting that we have seen earlier, this mixture of 3 Gaussians in 1 dimension. We have 1 Gaussian on 0, 1 on mu, and 1 on minus mu. And we assume that we have, suppose we essentially use k-means, that is a centroid-based clustering algorithm, driven by minimizing the Euclidean distance from each instance to its centroid. And suppose that we now want, only based on an empirical sample, without knowing the underlying distribution, of course, and using this idea of stability to determine whether we have 2, 3, or 4 clusters in the data. Okay, just a very simple example. And we're also going to assume that, mainly for analytical convenience, but it's not strictly necessary, that mu is large enough for the Gaussians to be well separated, and that the sample size is large enough to avoid pathological solutions. So we know, again, by the previous results, that these stability measures will converge to 0 as the sample size increases to infinity, both for k equal 2, 3, and 4. And we will show that actually a very, very simple empirical estimator of this stability measure can clearly distinguish between them and find that indeed we have 3 clusters in the data for any sample size, no matter how large. So if you want, this is essentially a proof of concept that the results from the 2006 paper are indeed not the end of the story. And in the end, I'll also discuss how this result can be generalized. I should also mention that the stability estimator I'm going to define in a moment is essentially similar to what stability-based algorithms do in practice. It's just more naive and more simple. So if this thing works for this estimator, then it would undoubtedly work for real stability-based algorithms, and we're going to see evidence for that later on. Okay, so how do we define this empirical estimator? So it's very simple. So for convenience, we assume that it works on slightly larger sample sizes. So it estimates the stability for samples of size m, but it actually uses a sample of size 4m. It's not really a problem. So it takes the sample, it split it randomly to 4 disjoint subsets. It takes 2 of the subsets, cluster them, and directly estimates the distance between these 2 clusterings based on m sample pairs drawn from the other 2 subsets. Okay, so if the stability measure talked about this expectation of the distance measure, we're just going to compute it on a single pair of samples, and instead of the probability over instance pairs, we're just going to take n instance pairs and computed completely empirically. And what we can ultimately prove is the following theorem, that if we indeed calculate these three stability estimators, then the probability that the most stable model is not going to be k equal 3 is upper bounded by something which is exponentially small in the square of mu, the separation between the Gaussians, and the square root of the sample size. So essentially what this theorem implies is that our probability of making a mistake is upper bounded by something which doesn't increase with sample size, but actually decrease with sample size, converges to something which depends on the separation between the Gaussians. I should also emphasize that this asymptotic notation with the omega is not to hide any huge constants. It's just in order, so I could write the result compactly, and so I can conveniently ignore small second-order terms. I won't go over the entire proof, but the basic idea is that we first of all show that the stability measures for this distribution indeed have this condition that the ratio between them for any sample size, both stability A2 to A3 and A4 to A3, is larger than 1 by some positive constant C. From this, we can show that if we actually just take a single pair of samples, instead of this expectation over sample pairs, then still with high probability, the ratio between these distance measures is going to be larger than 1 by some positive constant. And then we can simply apply our theorem, which we presented earlier, to show that indeed the empirical estimators of this distance function would be able to discern the more stable model with a high probability for any m. Now, I would just like to show the first part, because it has to do with something I would like to say later. So the first part is, as I said, to show that we have this constant ratio between the stability values. So we essentially lower bound the stability for A2 and A4 and upper bound the stability for A3. You get something which looks like this. And just to make it more concrete, if, for example, I take mu equal to 7, then we can see that indeed the stability for A3, for the right number of clusters, so to speak, is much, much smaller than the stability measures for A2 and A4. And it has this ratio which doesn't depend on the sample size. They all go to 0 by something like 1 over square root of m, but the coefficient is quite different. And why does this thing happen? So let's look for example, on what happens for k equal 2. So for large enough sample sizes, the centroids that we're going to get will fluctuate around alpha 1 and alpha 2. Okay, we take a sample, we cluster it, we look at the position of the centroids, and now we can look at the distribution of these centroids over samples of size m. So the centroids are going to fluctuate around alpha 1 and alpha 2, and the border between them would fluctuate around the point beta, which we have here. And the same kind of thing happens, for example, for k equal 3. So we'll have, in this case, one centroid in each mode of the Gaussian, or at least in its close environment, and the borders on beta 1 and beta 2. And the main idea is that we can show that for large enough samples, the borders will have these small fluctuations, with more or less the same order of magnitude, but the area over which they fluctuate is very different. For k equal 3, it's going to be in an extremely low density area, while for k equal 2 and k equal 4, the borders are over much higher density areas. So if you recall, the stability measure essentially has to do with the probability mass which switches between clusters. So although these fluctuations will become smaller and smaller because the areas over which they fluctuate is different, we have this ratio between the stability measures which doesn't depend on the sample size. Okay. Now, so as I've shown for this simple example of 3 Gaussians, indeed stability works despite this convergence to 0 for all the k's we consider. But of course, the most obvious question is, can this result be generalized to more interesting cases? So, yeah.
Wouldn't it be sufficient to look at the borders and just try to determine the number of samples that fall on the borders? Wouldn't that be a better, well, an equivalent metric of deciding stability?
Yeah, well, that's a good question. And well, as I'm going to speak in a few minutes, it does seem that this issue of the density that you have on the border areas is perhaps the dominant factor affecting the values of the stability measures. But first of all, our approach is really to explain the algorithms that are used currently by practitioners. It's an interesting question, and we are currently looking into that, whether we can use these results in order to devise an algorithm which, for example, as you say, just look at the boundaries and try to see what is the density there. It's not completely trivial because when you're talking about high-dimensional data, etc., it's not very easy to estimate the density along the boundary points. So you can do all kinds of estimations, and we are currently looking into that. But right now, we just focus on understanding the algorithms that are currently used. Okay, so the proof that we use for this simple example of this mixture of 3 Gaussians, so what we really needed in the proof was not something which is too dependent on the specific setting. What we needed was that, first of all, clusters are high-density regions with low density at cluster boundaries, so that these fluctuations of the boundary points is over low-density areas. We needed the fact that the stability measures converge to 0 at a rate which is slower than 1 over m to apply our statistical theorem. And we needed this assumption that expected values reflect the typical case. That's what allowed me to, instead of talking about expected values over sample pairs, to just take a single sample pair, and still this ratio would be reflected with high probability. Now, in a recent development, which I should emphasize is not in our current NIPS paper, we have been able to, indeed, to generalize this result and show that a similar behavior actually occurs for more or less any distribution in Rn, obeying some very mild niceness properties with the k-means objective function. So, indeed, essentially, the most important or dominant factor governing these stability measures is the fact that the boundaries between the clusters have a low density. And it's an important point because up till now, okay, so there were these various stability algorithms that were developed, but there wasn't really any understanding of when this notion would work, or to what kind of assumptions correspond the use of this technique on our data set. So what we essentially can say is that if, for instance, you want your clusters to be separated by low density areas, this is the notion of clusters as far as you're concerned, then cluster stability would be an appropriate method, at least if you use the k-means algorithm. Yeah. Mm-hmm. Right, so for k equal 3, you'll have a relatively... No, you would have... Okay, the density won't be exactly 0, but it would still be much relatively lower than if you look at other values like k equal 3, etc. The important quantity for this more general result is essentially the integral of the density over the boundary areas. So And the question is the relative values. It is possible that for any k, this value would be absolutely large, but if for a certain value of k, this value is going to be lower, then this would be the value of k. This kind of cluster of stability techniques would tend to give you as the answer to how many clusters you have in the data. Yes? Yeah, so okay, so first of all, this claim here, as I say here, is with the k-means objective function. Okay, so if you have a data which k-means algorithm is not good for, or more importantly, if your notion of clusters is different than the notion that I've just described, then yeah, so both k-means and using k-means with for cluster stability would probably fail. So, and we are currently working on further extending these kind of results to other objective functions, such as with spectral clustering algorithms, etc. But it's still a work in progress.
But does it go back to the issue that k-means just can't find, is not really reliable at finding the global optimum for some distribution? Is that the reason? Would that be the reason for explaining?
No, because even if you have this distribution which looks like two moons, etc., then k-means would have some optimal solution. It might not correspond to a partition of one moon in one cluster and the other moon in another cluster, but there would be some sort of optimal solution. Okay, so. Yeah, I mean, obviously also the selection of the clustering algorithm which you use for cluster stability matters a lot. You would want to use an algorithm which is capable, at least in principle, to catch the kind of clusters you want. Okay. For if I use it on moons or something like that, well, I guess it would be more or less the same. Actually, I guess the stability measure would tend to increase as you look at larger k's, because if you look at the integral over the boundaries, if you have a larger value of k, then you do an integral over a larger area. So in general, I would guess, you would guess just this kind of trivial thing where k equal 2 maybe would be more stable, but not because you have two moons, but just because you have a smaller area over which you integrate. We're going to see some example later of, I mean, both cases where stability works and where it doesn't work, and you can really apply this sort of intuition we developed to understand when would it work and when it would not. Okay, any further questions before I continue? Okay. Okay, so let's look at a few experimental results just to see the things we've discussed. So first of all, we ran some experiments for exactly this distribution that we've worked on, this mixture of one-dimensional Gaussians. So on each row, you can see on the left the distribution. In the center, we have the values of our empirical estimators averaged over many trials. And on the right, we have the failure rate, or the percentage of trials where k equal 3 was not returned as the most stable model. And you can indeed see that exactly as our results predict, the failure rate doesn't increase with sample size, but rather stays more or less constant at a value which drops off very quickly as the separation between the Gaussians is increased. And we can also see in the center plot that we have this converges to 0, but at a constant and different rates. Now, as I've said, it's also interesting to use our results to see when would cluster stability, when it won't work. So the first case, we have here. So I simply took the 3 Gaussians and put them much more closer together. In a sense, one of the Gaussians is absorbed into the larger one. And we can see that in this case, k equal 2 is returned as quite consistently as the most stable model. So in this case, we can say that this is probably also what we would want. But we can also look at the second example below, where in this case as well, k equal 2 is returned as the most stable model. So what we did here is take 2 of the Gaussians and relatively separating them from the third rightmost Gaussian. So why here? So why does the stability measure returns k equal 2 as the most appropriate number of clusters? So it's exactly because for k equal 2, the boundary between the clusters is on a low density area. So we can see that in these kind of clustering situations where we have this sort of nice hierarchy, the stability measure would prefer to return the lowest value of k, which is consistent with the hierarchy. Again, this might also be a reasonable answer in a certain sense, because at a certain level we can view this as having 1 cluster on one side and 2 clusters on the other side. So this might suit what you want, or it might not, but this is what cluster stability does. Yeah? Sure.
So if you were to run isolation, for example, on this, wouldn't you get 3 clusters from the 2 examples at the bottom, and isolate maybe being a bit confused on the number of clusters for the top one? I mean, my question is, does this bring anything? Because if the clusters are well separated, something like isolate would give you the right number of clusters anyway.
Okay, so if I agree that if you have an extremely well separated data, then most proposed model selection techniques would work. Again, our approach here is a bit different. I mean, I'm not trying to sell you cluster stability as the best technique there is always, and you should use only that. I'm not. I mean, the issue of model selection in data clustering is a very difficult question, and there isn't a single technique which is, amazingly good and much better than all the other alternatives. All I'm trying to do is take a certain algorithm which is used quite a lot by practitioners and seems to work pretty well in practice, and try to understand it theoretically, really understand when it would work, why does it work, etc. Okay? Okay. Finally, we also did some experiments on more complicated distributions. So if we look at the first row here, we have a random sample from the distribution. The clustering algorithm running in my brain tells me I have 5 clusters here. And the stability method works as well. It tells me quite consistently that we indeed have 5 clusters in the data, and you can see that the failure rate indeed doesn't degrade with sample size. I should mention, by the way, that the stability method used here is not the estimator we've defined above. We actually went and took a stability method from the literature, which is much more complicated, does all kinds of bootstrapping techniques. But we can see that the same phenomena occurs, that we usually have this convergence to 0, but at different rates, and it prevents the stability algorithm from degrading with sample size. In the middle row, you can see another case where we went and took not a k-means-like algorithm, but a spectral clustering algorithm. And again, exactly the same phenomena of convergence at different rates, and the failure rate doesn't increase with sample size. And in the third case, we have real-world data. This is, of course, a low-dimensional representation of it. It's a phoneme data set. Each instance is a recording of an English speaker saying a certain phoneme in English. And the stability method returns k equal 3 as the most stable model, which is a reasonable answer for this data set, because if I would have removed the colors, I think you would also see 3 clusters here. The point is that the vowels tend to form a single cluster relative to the other phonemes, so we get something that looks like 3 clusters. Yeah.
Can you use the failure rate to derive some form of confidence in the number of clusters?
Yeah, you can do that. The only problem is that in the end you are limited to a certain finite sample size. So indeed what the stability methods do in practice is to bootstrap, to take random sample pairs many times over and try to use that to estimate the stability. So the more data you have, the better it would work, but you are fundamentally constrained in that you have a finite number of data. Yes?
Typically something like a bag of algorithms they want to try.
Mm-hmm.
A bunch of high-dimensional data that they can't do. So if you plot different algorithms for the same data set,
Mm-hmm.
it's the same thing where like one particular picks out k equals 3 and the lowest line.
Mm-hmm.
Does that tell you that that algorithm is probably putting this data better?
Mm-hmm. Yeah.
I would get a crappy cluster.
Mm-hmm.
I presume you have plotted
Yeah.
the stability index would be higher up than the k equals 2, but
Mm-hmm.
not the correct cluster. I'm just wondering if you can use that to also pick the algorithm when you can't visualize the data.
Yeah. Well, it is possible, but well, it might be possible. It's something that we hadn't checked. Tell you truthfully. Any further questions? Okay. Okay. So in conclusion, what we essentially did in this work is to demonstrate that the relevance of cluster stability is essentially determined by the exact rates of convergence rather than these asymptotic values with quantifiable criteria. An interesting question is that, or point is that if we take these stability measures and do an appropriate scaling, such as multiply it by square root of the sample size or something like that, then what we get is not a convergence to 0, but a convergence to a certain finite positive value, a sample size free stability measure, if you will. And it's a very interesting question that we're looking on right now, is to understand what governs these sample size free stability measures. Again, as I've said earlier, it does seem that the most important thing is this integral of the density, but there are also some other things that go into there. It's an interesting direction of further research. And again, as a proof of concept, we've shown that stability indeed can work for arbitrarily large samples, despite what could have been concluded from the 2006 paper. But moreover, the results can also provide us with insights for practical sample sizes as well. As you've seen in the experiments, that these kinds of different convergence rates was not just for extremely large samples, but for very moderate and reasonable ones. And we believe that these kind of insights can indeed work for practical sample sizes and not only asymptotically large ones. That's it. Thank you very much. Okay, thank you.